and Don Banfield. Oh, I'm sorry, that's not the right one. They're in 4. Tim Titus is the in-room chair, and Kai Williams is the remote chair.
Yes, I'm the in-person moderator. Testing 1. All right. I'm Tim Titus, USGS, and my online moderator is Kai Williams, also USGS. Kai, are you there?
Yes.
Good, great. So Kai is going to keep me honest when it comes to the online folks. We also are showing our questions so that we can, hopefully in real time, catch those questions. So the first thing is we're going to go through the groups. And I think we'll start with the online folks. So Kai, if you want to introduce the first group to back brief what was discussed. There was no online group?
Yeah, they had 2, 3, 4.
Oh. Okay. All right. So I understand there was no online group. Anyway, so the first thing, it will be the dust lifting group, which, if I remember right, was combined with group number 4, alien flux measurements. So if they could come up and present their results or their overview.
You got the notes.
What were the prompts again? Top 3 challenges, new measurements. So we didn't get through all the prompts for this, but we sort of went over the specific measurements that we should be collected together. It's mostly what we got through in the time we had. For dust, we talked about you want to be able to detect the dust itself. So you can get dust concentration and a size distribution as a function. Both of those as a function of time. There was some question of whether measuring directly the velocity distribution of dust was critical or not. So that was open-ended. But then along with measuring the dust directly, you want to also get wind measurements, because ultimately you want to get a measure of the dust flux, particularly the vertical dust flux. Assuming in this, and this is one of the assumptions we had, is what we want to understand is what is driving dust lifting, the dust emission into the atmosphere. So you want to try to measure that, and the reason that's why vertical was we thought was more important. So although we still debated amongst ourselves if it's completely more important than horizontal, but understanding the dust coming off the surface locally to try to understand the conditions. So that also meant that you also wanted to understand what the environmental conditions are. And we discussed that understanding the convective conditions in the atmosphere would probably be most important to try to test the ideas of what drives dust lifting. Because I believe the ideas are it's dust devils, saltation, and then some hand wavy words around dust storms driving the lifting. But it seems that at least the devils and the dust storms are related to convective processes. So if you start to see dust emission coming up, and you can correlate it with convective processes. So that also argued again, measuring the wind, but maybe with like a sonic anemometer where you're getting the fluxes, so you can derive the turbulent kinetic energy and maybe even a sensible heat flux throw in. Now we're talking about throwing in at least a simple hot wire temperature sensor or something like that. So it's about pulling all the pieces together to get the environment, so then you understand why you're getting increased or decreased levels of dust in the atmosphere where you're measuring it. And we also talked a little bit, would all that be sufficient, or do you need to complete energy balance at the surface? So also getting the radiative fluxes as well. And it wasn't in our discussion completely clear if you absolutely needed that, or if just understanding the convective conditions would be enough. And all of this connects to understanding saltation, which we'll talk about later. And I don't think we got to the other prompts. Oh, we sort of talked about, are there specific instrument types that would work better? The feeling was that the way we've done the dust concentration and size distribution measurements in the past by using upward looking cameras or radiometers, and then trying to derive the column opacity with some modeling, that's not sufficient to get the dust flux out of the surface. It's really the flux that's more important if you want to understand what's going on with lifting. All right, that's all I got.
All right, now I should be on. All right, group 2, surface roughness to topographic change. Who is the speaker for that?
Oh, I'm sorry. Jack, do you want to talk? I'm sorry. Okay, yeah, we. I think I stepped on Jack. He was going to lead this conversation. We talked a little bit about this problem, and I don't know that we got past the first prompt because we realized that we weren't completely clear what it is we wanted to measure, and whether the conditions on Mars were always right to measure it in the way that we often measure it. So this is maybe a question for some questions for Don and Jim, who I see are online. One of the issues that came up was when you're measuring shear on the Earth. Brian Jackson, yeah, by the way, Brian Jackson in the room here. Very often, you'll measure shear stress by fitting that law of the wall wind profile. But that law of the wall assumes that the conditions are turbulent where you're making the measurement. And specifically for turbulence, the Reynolds number has to exceed some critical value, which depending on who you ask is something like 2,000, 2,300. And so we started wondering whether that condition was always going to be met at the surface of Mars, because Mars has a much higher viscosity in its atmosphere. And so Jack and I put together let me just share my screen real quick. Jack and I put together a chart showing Mars Reynolds number as a function of velocity here on the leftmost column, and then length scale of interest along the top row. And then each of these, I am sharing it. Yeah. And so then we see the Reynolds number there among the columns and rows, and then I've color coded in the entries which in principle are above the critical Reynolds number. And so what we found was if you're thinking of a length scale of 1 meter, then you're going to need velocities of at least 3 meters a second to be in this fully turbulent regime. So I guess one of the questions we had, and this may be something that Don and Jim can answer for us, is what is that length scale referring to specifically, right? Is that the height of the anemometer? Is that the scale of the surface roughness elements?
My scale of interest would be the size of the cobbles and pebbles and which you want the flow going over that, and that's influencing the turbulence because it's adding tripping the boundary layer or whatever you want to say. So if your surface roughness is somewhere between, you've got cobbles or whatever sitting on rocks of 10 centimeters high, littered across the surface, that sort of says you got to get pretty high winds to get fully turbulent flow.
So I guess thinking about sort of measurement requirements and issues that Serena asked us to think about. What this is suggesting to us is that you need to choose your locale very carefully, so that you need to have the right kind of length scales. Yeah, thanks, Don. That's a really good point too. Right. Law of the wall also assumes that the atmosphere is neutrally stable, which isn't always true either. So this is telling us, I think, that if you're going to make a measurement of roughness using the law of the wall, which is, I think, something we've come back to several times during this conference, you need to choose your locale very carefully so that you have the right roughness already. And you need to make measurements only when the wind speeds are high enough and when the atmosphere is neutrally stable. Otherwise, trying to fit a law of the wall profile to estimate shear is not going to work. Use particle Reynolds number. Doug, could you maybe put a link? Is there a good reference for that that you could point us to, the particle Reynolds number?
Well, yeah, there are lots of them. It's basically a function of U star and grain size. The length scale, of course, is tiny. You can assume that shear velocity is on the order of about 1/10 of the wind speed. So the numbers are very different. I'll go ahead and find some simple reference and I'll copy and paste it into chat for you.
So is this telling us that, is all of this telling us that measuring surface shear using law of the wall on Mars is not a thing that we should do? Okay, so maybe I'll just stop there and let the next group, the online group, talk about their discussion.
All right. I have a feeling we're going to circle back to surface roughness and neutral atmospheres again. But so we'll move on to group 3, understanding volatile exchange.
Thank you, Tim. So we've discussed not only planets, but also one planetary body, the moon, which has a slightly different atmospheric conditions than, for example, the Mars or Titan that have at least some atmospheric vapor pressure. I'm going to start, though, with our discussion about Mars and potentially Titan. We've discussed the various instruments that could go on a lander that would land on the surface of Mars. We discussed the possibilities to measure the ground humidity, if there's liquid water, or just ice content if there's no liquid water, by, for example, drilling and measuring soil moisture, by, for example, measuring relative humidity, drilling and measuring relative humidity. And we've asked the question, what do you need to make the same measurement on Titan, for example? Of course, not to measure water, but to measure other liquids there, like methane or ethane. Yesterday in the field, we've seen that dunes can be complicated to measure. So, for example, if this lander would land on a dune, Tim mentioned that ripples that they've noticed in experiments, that ripples that move along the throughout the experiment change the depth of the region they're looking at, basically, which would potentially make it more difficult to measure and would require adding another measurement of the depth of the height of the surface, of the depth of the layer that's being looked at. We also thought about potentially producing instruments that could go on the less used or less employed part, or less the parts that are less used of the instrument that we saw yesterday. So, for example, the arms of the instrument instead of the mast. If we could get some of those instruments on the arms instead, then it could, of course, would make more sense to place them on Mars. And then on the moon, we've discussed how we can measure similar interactions between ground ice, which exists primarily in permanently shadowed regions near the pole, and atmosphere, kind of continuing the lightning talk we heard this morning. And one proposal was to, or one suggestion was to heat the upper layer of the lunar regolith in a location that we know from previous measurements, such as Cabello's crater, to contain relatively large amounts of icy regolith. So not pure ice probably, but icy regolith, which was measured to be, if I remember correctly, about 8% by mass in the L-cross experiment, by weight. And then heat this regolith and measure the vapor pressure, basically how many molecules escape the experiment area, the heated site. And from that, maybe say something about the amount of volatiles in the subsurface, in the near subsurface. And unless anyone wants to add anything.
Yeah, I don't see any questions for this group. So yeah, let's, can we go back to the online group number 2?
Want to keep with volatiles and have that group scope?
Yeah.
So
So we'll do online group number 3, and then we'll swing back to number 2.
Okay, so this is Don Banfield. I was volunteered to kind of represent our group. I didn't actually take notes of who was in the group, but we had like 8 people in a pretty lively discussion. I don't know that we hewed very well to the thought prompts, and I apologize for that. We didn't really talk at all about Titan and ethane and methane or sulfur on Venus. We did talk a bunch about water and a little bit about CO2 and some about methane on Mars, but mostly we focused on water. We talked about the potential of using, say, the upward-looking dial instrument that was discussed in the lightning talks to get water abundance in the bottom, say, 5 kilometers as a function of time of day, and how you might be able to use that alone to infer the flux of water between the surface and the atmosphere. We also talked about potentially directly measuring it with eddy covariance methods close to the surface, or also having profilers of a couple of tunable laser spectrometers, some very close to the surface, say centimeters, others a meter up or something like that. And I think all of those sounded promising, but we spent a lot of time also thinking about, yes, you can look at what it is happening, the flux that may be happening in the atmosphere, but you should probably also be at the same time trying to measure the, say, soil moisture directly in the soil. And unfortunately, none of us in the group had tremendous experience of exactly how you would go about doing that. We dug up a couple of abstracts and saw that there were permittivity measurement approaches. We talked about maybe there's remote sensing, like submillimeter sounding approaches that might work. But I guess the takeaway from that was that you'd have much more confidence in your inference of, say, water exchange between surface and atmosphere at Mars if you both measured it somehow in the atmosphere and also from the soil. Let's see. We talked a little bit about whether you could use something like the mass specs or enrichment cells that are, for example, on MSL. And I think the way that's been implemented, it's not really feasible because you really do need the diurnal sampling. But there may be ways that you could modify an instrument like that to take multiple samples during a day and analyze them later. Oh yeah, one of the reasons that we felt it was not ideal just to measure what's going on in the atmosphere alone is that from a single point measurement, it's difficult to assess whether there's lateral advection into and out of that place where you're sampling. And so that's one of the motivations for why you'd want to simultaneously measure what's going on in the soil itself. And then right at the very end of the conversation, we talked a little bit about habitability, and some of the measurements you might want to make with that, like the temperature of brines, and the water activation, I guess, in the brines. And that's about all that I have to report on that. So if others have things to add that I failed to report, please jump in.
Anybody, any questions online or comments? Any questions here live, or I should say in person? All right, I think we'll move back to group 2 online. So take it away.
Hi, so I was put in charge of doing some summary. We were the J group. So Jim, Joe, Joanna, Joel, and myself were in this group. And in contrast, or in relation to what seemed to be discussed in the in-person group, we kind of had a back and forth on how to measure roughness and what to measure it for, and coming up with kind of two large groups. One is taking this aerodynamic approach. The other is taking a much more kind of geometric approach. So Jo Neal talked about her experiences using terrestrial laser scanners to come up with geometric roughnesses, and then we've actually worked together on kind of validating that for aerodynamic roughnesses with some success, although I'd say limited success. So there is a procedure there for converging that geometric measurement, which is, you know, perhaps the same thing that you would have to do with some assumptions if you measured it aerodynamically. But one advantage of taking the geometric measurements is that the errors associated with those measurements are well known, whereas any measurement errors and the propagation of those errors from the aerodynamic measurements are relatively large and less well known. And so there was considerable advantages associated with using a geometric measurement, however that may be done, over the aerodynamic one for those reasons. In addition, at least a terrestrial laser scanner could be shared instrument. And so some of the instruments that were discussed in the lightning round earlier that were looking upwards, perhaps if there was a way to have them looking downwards at the ground, could then be utilized for these types of measurements. We discussed also using photogrammetry for some of these measurements. That obviously has worked well in the past, but unfortunately there's some limitations, especially during transport processes, and so they were generally used for passive, but they're also very limited in terms of their range of roughness scales that could be measured. And then lastly, associated with that kind of topic is this sort of identification and assumptions of the range of roughness scales that need to be measured and how that would influence your placements of instruments, whether that's sort of on the surface spatially, also vertically on a mast or relative to the ground, and how that may need to change over time depending on the amount of transport that's occurring and how to deal with the effects of that. And so what was raised was perhaps there need to be some identification of projects in analog sites where some of these factors are played with, or within a model, so then we could have a better understanding of how that may affect the measurement compared to the measurements that we can make normally here on Earth. I think that's it. So if anyone has from the group, if I missed something, please add that on.
All right. At this point, we can open up.
There was one more online group. If you want to give your report, I think it was the dust and sand mixed. Group 4.
Good morning. It's my privilege to report a summary of the Group 4 discussion. For this conversation, we more or less ignored things for the large part, like power supply, weight, how the data would be handled, and we ignored quite a bit about reality. Part of our challenges that we did consider are durability of the instruments, and we assumed that dust accumulation on the instruments is a potential problem that could prevent efficient performance. So our recommendations for the type of data we need in the instrumentation: vertical array of 3D sonic anemometers, so that will allow calculation of Reynolds stresses at a variety of heights. If that is successful, it obviates the need for measurements of surface roughness with regard to sand transport. We think that it should be reasonably expected that we can develop strain gauges that are appropriate for the measurement of surface or near shear stresses. These can be deployed at a number of elevations. And although I don't really understand all the technology behind it, Myring discussed a version of strain gauges that can also have verticals that are sensitive to saltation index. And so when I'm done with this overview, if there are more questions about that potential, I'm going to direct them to him. He also discussed a device involving bodies where grains of only certain sizes will have enough momentum or inertia to impact bodies rather than be deflected by around them. So these are used to detect saltation and sizes. We also want to mention again the potential importance of measuring the electric field. We know that when dust is present in the air, there is a huge static charges can develop, and we know that those can have some effect, unknown magnitude, on saltation. And finally, the need to have a camera. Now, a camera for a couple of roles. One, for high resolution imagery of the sand surface, so we can use some photo sieving software to make grain sizes and distributions, and also the possibility of high-speed cameras to capture saltation trajectories. We want to use that last as a substitute for particle image velocimetry. We love the array that Christy Swan has described. Can be shrunk down to a suitable size, then that would be far preferable to what we're talking about. But these are things that we think might be possible. So thank you for your attention. Questions?
All right, I don't see any questions. We'll roll back to Alejandro. I believe he's got some additional on-site input on the topic of alien flux measurements.
Yeah, so Lori, Lauren and I talked a little bit about this as well, and I think it's complementary. In terms of instrumentation, it's similar to what you have, piezoelectric. We didn't talk about strain, but that's related to it, or optical gate or laser backscatter, which has been discussed this week. But then we talked a little bit about measurement types to take together, and not just the measurements for the direct detection of the saltation, but what you need to know to understand the environment that's going on. So you want to directly measure the saltating grains, which Douglas summarized pretty well, some options for doing that. But then also we were talking about how we also want to understand, well, ideally the wind profile in a saltating cloud to understand the dynamics associated with the individual saltating grains. but then also measure the wind shear above that cloud to understand the kind of general boundary layer environment that is generating these saltating events. And to go with that, the air density, temperature, and surface roughness are also probably other things that would need to be measured independently somehow or derived to provide you the big picture. Because where we thought we wanted to go is you wanted to derive the saltation threshold. That would be something that if we could understand what that is on Mars, that would help our physical understanding, but also help us then as an input into modeling for other phenomena not directly related to saltating, like the dust lifting threshold and other stuff. So that's what we discussed.
All right. Any questions on the sediment flux? All right, I think we'll go into sort of a general discussion, general questions. So pick your favorite topic.
All right, so this is Serena. I was running around a little bit during the reports. There we go. So I may have missed this. Doug, I know in your group you guys had talked about durability of the instruments and collecting saltation measurements. I'm now thinking maybe the approach there, because I brought up a typical baseline we're looking at is at least a season, if not a whole Mars year. So that's a long time to be operating one of those sensors. And if the sensor in the saltation cloud is going to be destroyed by the saltation cloud itself, maybe what we would need to do is make sure we have complementary measurements, something that would be up higher. If we could do it from camera, it's not as good, but then for at least for a period, we can get the better resolution information. We can calibrate between them. And then whenever we lose the better measurement, we still have the I'm going with camera because that's what I'm familiar with, but something that is less likely to be destroyed by the saltation as it's going and is a little bit more remote.
That's a great concern, Serena. Can I ask you a question about that?
Mm-hmm.
How happy would you be if you had 10 minutes of high quality saltation data from Mars?
I'm going to turn that to the people who actually study this. How happy would you be with that? And especially if we could calibrate that then with maybe a much worse measurement, but one that would be longer lasting. I think it'd be awesome just because we don't have it, but.
To respond to Doug's question, this is Alejandro. Whether we would be happy in this room with 10 minutes of good saltation data or not, I don't think NASA would be for the cost to get there. So I think we need a solution that definitely lasts a lot longer than that.
Hi, this is Jack. I have a comment on the durability or a comment question. Because saltation happens much less regularly on Mars and in a sandy environment even, I suggest that eases the durability. It enhances our ability to engineer something that may be more robust because it's not going to be impacted as if you had it on one of Doug's beaches where it's going to be hammered. On Mars, that's not going to be occurring as often.
Yeah, and I would add that, on Mars, it's likely that the saltation layer may actually be much higher. And so I would say having multiple your array extended so that you're catching the very top. And those are likely to survive even longer. And so even if you lose some of the bottom sensors, you can then go back, look at the historical profiles, and then extrapolate.
And I'm glad you brought that up. One of the issues that I forgot to raise because of my poor note taking that James King did bring up, and that is that piezoelectric discs, although they're buggers to calibrate, are relatively durable and very inexpensive and very light. Part of our durability issue concerned contamination by dust, not the physical destruction of the instruments themselves, but the reduction or elimination of their viability or performance, rather. They're not alive.
So it sounds like you're saying that, with any instrument, one has to be careful about instrumental drift in its calibration. And that should be part of the plan.
Just with that in mind, I want to re-raise a point that Ralph Lawrence had raised on Tuesday, which is he always tries, this is more for terrestrial experimentation, so it's a little harder to do for planetary, but he always tries to plan for 3 ways to make the same measurement. And you pray that at least 2 of them work.
So on that note, Serena, actually, I will throw in, when I showed up my abstract, we had our normal weighing BSNEs that, had a load cell. You could look at the voltage, see how much weight. But we also had one that was a high volume that really was just taking pictures of the volume. And so completely different system, measuring something slightly different. So not mass, but volume of the sediment. And it turned out that when we had failures, or one case, the storm was so large that the sediment flux overwhelmed our smaller BSNEs, our high volume one with the camera saved our bacon. And we were able to essentially estimate that the flux during that storm was 10 times larger than our normal high flux storms. And so that's an example of having, different instruments trying to look at the same measurement in a slightly different way.
So Tim, you mentioned the kind of the relative flux in range of conditions. Do we have a sense of the dynamic range that we would be looking at on Mars with regards to sand flux or dust flux?
I think that's the question. I don't think we know. I mean, we've got estimates from migrating dunes and maybe from ripples, but that's a specific flux type, and it doesn't tell you anything about what was the upwind flux, what's the downwind flux, what's the difference. So, we're missing a lot of pieces in understanding the sediment flux balance. And I think, Joel, if you're online, do you have anything else to add to that?
Yeah, sure. Thanks, Tim. Tim and I have been working together basically on this issue of there are those basically orbital remote sensing based approaches like Tim described for measuring sediment fluxes. And that's what's done on Mars at this point, based on dune migration rates and estimates of dune heights from those digital terrain models derived from that orbital imagery. And so at the end of the day, you're talking about dune migration rates or ripple migration rates, and that gives you an estimate of your bed load, sand transport. But it doesn't actually tell you what this group is talking about, which is that saltation flux or dust flux, right, occurring above the surface. And so I think Tim and I have just kind of zeroed in on this need basically for terrestrial analog work to look at what is the story about these horizontal mass fluxes from saltation and then dust emissions that you're missing from that remote sensing approach. That's really the only tool that's been used on Mars at this point.
All right. Any other comments, or I think we have time for at least one more question. Yeah. Kai, do you have anything you want to add?
Nope.
All right. I guess at that point, I'll turn it back to Serena for the rest of the program.
No, thank you very much, Tim. We have another break. I know that it was a little offset with things, but we are actually back on schedule now. We do have a 10-minute break now. I'm going to ask that we take it because the online groups discussed through the last break for the most part, so they may want that time. We will reconvene in 10 minutes, and we have lightning talks on landing sites and mission concepts. And then we are moving into our next round of discussions focused on those topics as well. Thanks.
Okay, so we're gonna get started with the next lightning session. My name is Jake Widmer from UCLA. So up first, we're gonna have Don Banfield. Don,
Okay, should I take it away?
Yeah, go ahead. Oh, just real quick, I want to remind the presenters that we're gonna try and keep to 2 minutes, and then that way we can have a brief discussion following all the presentations, and that'll lead straight into the group discussions afterwards. So whenever you're ready, Don.
Okay, yeah, so Tony Colaprete's actually the PI on this, and there's a whole bunch of other scientists and engineers at Ames working on this. For a tagline, I've got that sentence near the top: a Discovery class mission with a temporally processing global coverage orbiter and a network of more than 18 globally distributed simple landers. That's kind of the catchphrase. If I just turn over to the orbiter part of this at the bottom, I just tried to put some figures that suggest that we're looking to understand, kind of the force and response of the atmosphere, the aerosols, the energy transport, the circulation. And we're doing that with this global coverage precessing. So it covers all of the local times, multiple times in a season, orbiter with a series of instruments on it that should do a quite good job. The really kind of key new one is a Doppler wind sounder that we're working on at Ames that has co-located wind measurements of horizontal wind vector, both U and V, with pretty good precision all the way down to about 5 kilometers from the surface, 5-kilometer vertical resolution and 10-kilometer resolution along track. And we also get temperatures and net solar and thermal IR, dust opacity, and trace gases. Turning over the lander networks, which might be more interesting to the folks here. These are relatively simple landers with a pretty big landing ellipse, 300 kilometers, access to plus or minus 60 degree latitudes. 1.5 kilograms is the total science payload though. So it's a pretty simple payload. Pressure, temperature, sky brightness, some trace gases. And we're talking about possibly including some sort of simple wind sensing approach, possibly some simple saltation sensing, and a local dust opacity measurement, like a nephelometry, that could let us say something about wind stress thresholds for saltation and dust lifting. At the bottom, I've got kind of a map of where you might imagine distributing these things and the current design of the probe, but that's in flux currently. That's it for me.
Okay, great. Thanks so much. We're going to move on to the next one, and then we'll come back to any questions or discussion afterwards. Richard Love, if you're online.
Yeah, just whenever I'm ready.
Yep, take it away.
Yeah, brilliant. Thanks very much. So this study was looking at the possibility to examine aeolian processes at sites on Mars that lack in-situ data. Obviously, despite the significant advancements in the number of landers and the instrumentation, there are vast areas of interest which lack this meteorological data. To examine such sites then, we propose a combined modeling approach using a series of integrated techniques to use a global circulation model fed into a mesoscale model, which ultimately informs computational fluid dynamics simulations. These CFD simulations then were performed at a sub-Dune length scale in order to examine the microscale wind flow processes. The study site selected was Nili Patera, the Bark and Dune field there, in order to test the ability of this approach to reproduce the conditions required to potentially contribute to the modification of the dunes, which has been observed there for almost a decade. In order to validate the model output then, we used the co-registration of optically sensed images and correlation software, or COSICORE, which has also been previously used to calculate dune migration rates and sediment flux rates. The findings then, very briefly, we found that at 3 of the 4 seasons, our combined modeling approach reproduces the sediment flux rates calculated from COSICORE by between about 1.24 and 1.6 times the COSICORE rates. This is across multiple seasons and about a dozen pairs of images. Further to that, we find that at 3 of the 4 seasons, our microscale modeling wind flow profile closely matches the actual temporal ripple displacement of the dune faces, which we can see in figure 2 and 3 here on the right of the screen. overall, then, this study has shown very promising initial results as a proof of concept. But to test it further, we're going to try it at other sites with high-rise data, but not in-situ data. But in-situ data overall would greatly benefit this approach with further surface roughness values, shear stress, and PBL measurements. And that's everything from me.
Okay, great. Thanks so much. Next, we're going to move on to Tim Titus for in-person presentation.
All right, so I am both polar and aeolian for Mars, and so it's like, what would be a great place to go to look at polar processes, but also might look at dunes, might also look at even gullies, but of course, trying to land an area that has seasonal CO2, it's going to get really cold. Things will probably break. It's dark. So the question then becomes, is there a place a little bit more hospitable, even just a little bit, where you can look at CO2 ice forming on the ground and subliming without being in the middle of it? And so the idea here was, what if you go to a mid-latitude dune field, such as Kaiser Crater, such as the one located on the east side of Kaiser Crater, and you land on a sun-facing equatorial or sun-facing slope, looking at a poleward-facing slope? Could you find a sweet spot where you can look at polar features, the CO2 forming on the dunes, you can look at the lee side of the dune, you can look at maybe even gullies forming from sliding blocks of ice or from other processes. And so it turns out that there's actually a spot on a small dune that's facing equatorial that stays CO2 ice free according to the models all year. And you can look at CO2 forming on the lee side, which is poleward facing, and you potentially see diurnal CO2 ice, potentially, and of course, definitely seasonal CO2 ice. There are likely some gullies here as well. So you could look at if these gullies are being modified by the CO2 processes. And so, so what I've got here on this chart here is just how much CO2 is on the south-facing slope based on the steepness of the slope. What are the temperatures? And then also on as if you're looking north or the sun-facing, what are the surface temperatures both day and night? And then also what's the peak insolation? And so the idea here, like I said, is really land on the small dune on a slope facing towards the sun, so you can watch the polar facing slopes doing remote polar science, but really close. And that's pretty much the bottom line there. Now, I picked Kaiser because that's what we were working on, but there might be other places that might be better. But anyway, it's a concept.
All right, great. Thanks so much. So now we are going to transition back online to Milan Krupa. Are you there? If you're there, you might be muted. Not there.
He's under something else.
Okay, we will go ahead and move on then to Ryan Wooley. Are you there?
Yes, I'm here. Can you hear me?
Yep. Go ahead.
Great. Yeah, so I think I'll be maybe shifting gears on everybody a little bit. Serena asked me to chime in with a little bit. We do a lot of thinking here at JPL about how do you get stuff to Mars, right? So, you have a lot of great concepts that and instruments that would love to take measurements at Mars, but it all hinges on being able to get a ride or get there in some fashion. And so this chart is one we share on 3 key methods to get small things to Mars, so on the cheap, so to speak. The first one, and ideally you would just piggyback with a bigger mission, right? Marco did this and DS2, and that'd be great. You're able to share the launch vehicle, perhaps even share the ride, the cruise stage all the way to Mars, and that can really enable low cost transfer. But the problem, as we know, is there are not that many things going to Mars that frequently. The only thing that we kind of have on the books is MSR at the latter part of this decade, and that is a long shot to carry any secondaries. So if you are relying on that, there it's challenging to find that ride. So then the next thing, the number two there is we know there's a lot of ride share going on at Earth, especially to LEO, but also to higher orbits, mini launches. So if you want to take advantage of that, you need to bring your own propulsion. So you get delivered to some Earth orbit, and then you turn on your propulsion and then get the rest of the way to Mars. And then if you're an orbiter, then you've got to hit the brakes at Mars and get yourself into orbit. So it requires a lot of propulsion, and so you want to get as far away from Earth as possible. So you'd want to start in orbits, beyond low Earth orbit. So GTO, the geotransfer orbit, or even a lunar transfer orbit, anything is as high energy as possible, so that you can limit how much propulsion your small spacecraft would need. And then there's a lot of concepts. You see this ESPA ring and how you'd be mounted, and the primary would be delivered, and then you would start making your own way. Now, the amount of delta V required to get to Mars can be quite substantial. So say you start in GTO and you want to go all the way to low Mars orbit. It depends highly on the propulsion type that you use. If you do a traditional chemical propellants, you're talking 3 or 4 kilometers per second of delta V, which means you're going to be 70-80% propellant, at GTO. So most of that mass in the ESPA ring, now ESPA rings can accommodate a few hundred kilograms of payload. Now, most of that is going to be dedicated to propulsion, and it's going to be quite challenging. Now, another key technology would be solar electric propulsion, which is much more efficient, but it flies different trajectories. You spiral in, spiral out. It takes much longer, but maybe you would get that down to your mass fraction, maybe 40% propellant in order to get to Mars. And also you're a secondary, so you're at the whim of the primary. You go when they go, you go to the orbit that they dictate, and it makes it much more challenging because Earth and Mars need to be aligned at the right time, and so you might have to do a lot of waiting. And the last one would be more ideal, is a dedicated launch. You have your own launch vehicle, but traditional launch vehicles are very expensive and would just clobber your budget. But we do know that there are a lot of small launch vehicles that are being developed that are promising low costs and much more competition. So one could envision that one of these that can do, let's say, 1,000 kilograms to LEO could, in theory, send something to Mars on the order of a few hundred kilograms for a much lower cost than the large launch vehicles that we have available today. But there's, that's subject to, the development of these new launch vehicles and their ultimate pricing and a lot of question marks with that. But we see a lot of promise in being able to have your own launch vehicle. That way you get to, select your own dates and launch conditions and go when you're ready to go. So that's it, what I have, but I am going to be around. And if anybody has questions, would love to talk to you about your mission concepts and ideas on how to get things to Mars cheaply.
Okay, that's great. Thanks so much. So it looks like we're still missing Milan. So if we do have a little bit of time for maybe 2 quick questions or a comment, I guess we'll get started with a question in the room.
This is Alejandro Soto. I have a question for Ryan. 7 or 8 years ago, some of us at SWRI were looking at sort of large N CubeSats, like 12 U's and 24 U's, trying to get them to Mars on a lunar transfer, off of a lunar transfer orbit. So looking at that solar electric propulsion, and we found one of the problems, of course, is getting enough solar panels on there to get enough power to it. But the other problem that seemed to be is the availability of the solar electric propulsion devices, the community building those, at least on the low end. I don't know if it's true in the upper end of ESPA. It was all very experimental. I know some of the companies that we looked at back then aren't even around anymore. Are you familiar of what that community looks like? Does it look like there's gonna be viable vendors to provide that size of electric propulsion motor for that option number 2 you have there? Because I think in terms of opportunity to go somewhere, that's the best one. But what I found is the availability of the right hardware with the lifetime and the TRL was the big problem.
Yes, that's definitely a challenge, and we have been looking at that extensively. And these challenges of multiple kilometers per second to Mars, throughput becomes a challenge. Now, we do see a lot in the industry of a lot of these startups that are building solar electric propulsion, but primarily aimed at station keeping and small maneuvering at Earth, hundreds of meters per second, and it's very enabling. But they don't worry about the throughput and the lifetime to do multiple kilometers per second, thousands and thousands of hours of propulsion. But there are a few that are being developed and look quite promising, and the commercial industry is driving the prices down. One that I'll point you to it is developed at JPL. It's called the MassMe thruster, and it uses magnetic shielding to enhance its total throughput and lifetime significantly. And then it's been licensed to a company called Exoterra, and they are developing that technology for significant throughput. Now it's kind of on the order of a kilowatt class. So for CubeSats, there's still, not a lot of high throughput, very lightweight ones, but I know companies are thinking about them. But as you mentioned, they're still low TRL. So, we're pulling for them, and we hope that the commercial revolution also pushes towards things that we can use for interplanetary.
Okay.
Did that answer your question?
Yep. That was great. Thanks. So if we have any more very, very quick last minute clarifying questions, looks like there's some discussion in the chat, but that might be a little better to bring up in the following discussion sections. Going once, twice. Okay, and I guess I'll hand it back to Serena now.
All right, thanks all. We're moving into our next, can we switch to the thought prompts? Thanks. So next discussion session. This one we are dividing into different groups. So I will pull up the slide. This one, originally when we were putting the program together, I had like individual discussion periods for each of these, and then I ended up just merging them all because it made more sense. Basically, we're now talking about kind of all the details of collecting the measurements. So we've talked about instruments, we've talked about what measurements are needed. Then we're going to talk about those nasty things like how do you accommodate the instruments on the spacecraft? You can't just slap it on anywhere, right? How do you pick your observation site? And how do you collect the observations, meaning operations? So there I'm meaning frequency and things like that. So next one, thought for discussion 4. Okay, so what we're going to do is divide into 3 groups. So site selection, where to place your spacecraft and collect the observations. It doesn't need to be one site. It doesn't have to be on the ground. Unfortunately, I don't think we got our helicopter experts into this meeting, but if anyone online or here does know about helicopters or drones or balloons or anything like that, you don't have to be on the ground. But think about where you would place your spacecraft. Consider orientation and proximity to specific features. Second group is going to be talking about spacecraft accommodation. So thinking about the different instruments we've been talking about and the different measurements needed, what are the measurement requirements and what perturbations do you need to be avoiding? And then operations, how to collect the measurements and return them to Earth. So consider data collection, when to turn on instruments, how often to collect measurements. And then please do consider data volume, which means data compression. Different ways of doing that. You can do summarization, you can do downlink prioritization, you could do some sort of environmentally responsive, but think about strategies for doing that. That's definitely a big one for our types of investigations. So online, these are the 3 groups: site selection, spacecraft accommodation and operations, and in room as well. So let's probably do 1, 2, and 3, and people can self-organize. We are discussing through, let me double check the schedule. We're going right up to lunch. So these discussions for at least the in-room folk can just merge right into lunch. We are breaking for lunch at 12:15 local time. Okay, any questions about that? Yeah, Tim.
So this is going back to discussion 3. If you were a note keeper, please send me those notes. My email address is ttitus@usgs.gov. So ttitus@usgs.gov, because I'll need those notes so I can put together a summary for tomorrow.
A good reminder. And for the people in the room, we have 1-page write-up of all the measurements that were discussed on Tuesday that we need, so you can use that as a guide. So, all right. If that's it, let's go into our small groups. Again, we meet till about 12:15 or so. Feel free to continue the conversations until lunch, and then we're reconvening 90 minutes after that. So it would be 1:45 local time for the plenary. Thank you all.